Hi, do you guys hear me? Hello?
We can hear you.
Okay. Yeah, I have a special arrangement here with the fact that Teams removed the capability of recording, and that's why I delayed the meeting. They said in a couple of days they will have another procedure, but it passed 2 weeks, and I don't want to wait, so pretty much I find out another way of doing it, and that's what I'm testing right now. So hopefully everything works fine, because I do want to have these videos recording on the internet as the other webinars before. You can see my screen? Not yet. Okay, let's see. No, right now. Yeah, do you see my screen? Not yet, huh? Okay, now it's coming, yeah.
Yep.
Good, yeah. Well, technology, I don't trust it. Yeah, let's start. So it's 12 o'clock. If anybody join after, is more than welcome. So this webinar is kind of a repeat. A long time ago I put this together in another way, and it's about the transformer bushing testing. If you have any questions, please ask the question. You don't need to wait for the end of the webinar. What we're going to cover here is some testing that were done on the MOT, and we will explain what they mean. So typical testing for the bushing are capacitance testing, power factor testing, tangent delta, and dielectric frequency response. So those are the four type of testing that we actually do, and they are interrelated. We're going to see how. Other elements like surge arresters and insulators, they may also be having some of these tests done in a similar manner. So what I'm talking about here, probably it does reflect those testing. So if you want to ask some parallel questions to not related to bushing but related to the surge arresters or to the actual insulators, we can compare that because they overlap quite a bit. So what's the purpose of this testing? is to prove the integrity of the bushing as far as there is no major leakage current, there is no damage, internal damage, external damage, there is no chipping on the skirts of the bushing, because that can lead to discharge with, we know all this ends up in a bolt fault and damage that is more major than can be stopped before is actually happening. So of course, when we reinstall bushings, we replace bushings, or when we change the we install a complete new transformer, this is part of the testing. This is a very important slide, so it's telling us what is actually power factor and what is the dissipation factor. So the power factor, you see here, the total current has two major components. One is resistive, one is capacitive, and those are actually forming those two angles. So we got the power factor is the cosine of the angle, Greek sine phi, is between the resistive leakage current and total current. So that's the actual dividing the resistive component to the total leakage current. You got the cosinus of the phi angle, which is the power factor, somehow similar to what we know from electrical circuits, but that's between current and voltage per phase. Here we talk about components of the total current leakage, the component on resistive side. The complementary angle of this, what is missing to 90 degrees, is the delta, another Greek sign, so the smaller angle here. And for that one, we have tangent of that angle, so tangent of delta, which will be the resistive current over the capacitive current. So those, please keep in mind this vectorial representation of the dissipation currents, because this is where we need to refer back when we do measurements. So what is the power factor? What is the dissipation factor? So somehow they use interchangeable. Both of them, we want them as low as possible, and then they are recommended values for different manufacturers, what they should be when you receive a new bushing, how far you can go with the bushing until a major change happens, and then you declare that bushing non-repairable. You need to take it out of use because these values gets over the limit that is acceptable for that manufacturer. Also a smaller change, some countermeasures that they recommend for a smaller variation of these two parameters. So again, power factor and dissipation factor. And then you will see that actually dielectric frequency response is reading these values at different frequencies. So basically is not a totally different test, is because this test that we call power factor and dissipation factor, it's happening at 60 Hertz. But then if we want to do this test at different other frequencies, then that become dielectric frequency response, which is narrow or large. We will say that in a following slide. So is also this reading affected by the temperature? So the temperature we want is 20 degrees Celsius. So anything that is not at 20 degrees Celsius is actually showing a different value and need to be corrected back to 20 for the compare to the actual rating on the nameplate of the manufacturer of the bushing. So we need the correction, which usually is done automatically by the instrumentation. There are methods to also calculate this if your instrument is not doing it and is an older type. Also humidity may take a little bit of a toll on this one. A fast change, like a sudden change in these values, also is a concern. So not only the limit where you are, but the trend showing definite change over 5% over a short period of time. Any questions about the power factor in a bushing, which is not different from any other insulator? So these definitions that we talked about here really apply to any type of insulation, is not specific to the bushing. The way the test is done is specific to the bushing because it takes in consideration the form, shape, and distributed capacitance. We also have capacitance, right, the 4 test, which measure the capacity in percentage, as we're going to see, is C1, C2, and C3, depending where you have the measurement taken from. Any questions for these 2 parameters, power factor and dissipation factor, and then what angles they actually defined from the leakage resistive current and total and capacitive current? Any questions? Okay, so I'm stopping at this slide a little bit more than I will at the others because it's very important to refer that back to this one. Another way of defining this tangent delta that you saw before is through the material electrical permittivity, and then you have, in the same way, you have the actual tangent delta defined by the complex over the real part of the permittivity of the material. Okay. Next slide is a bushing equivalent diagram. So any bushing can be seen theoretically as something that is made up of a series of capacitors in between the skirts of the bushing, and then in the middle you have the actual center conductor going from the transformer connected to the windings up to the top, where you have the lug connection for the cabling that is coming to the transformer. In between you have a ground flange, because the actual bushing, they go through the tank and they come from the windings up to the transformer in the air where the cable will be connected. On the bushing, so is a little bit of stress happening in that point because the electrical field gradient over there is 0, right? The tank is connected to the ground. On the other side, on the right hand side, you have the tap electrode grounded layer. So this is a flange. We're gonna see at the end how it looks with some pictures. Is where you have the tap for the testing and reading purposes. Another representation of total capacitance. So we will not measure individual capacitance of these skirts. We will measure a total capacitance up to the tap test, and from the tap test to the ground is C2. So C1 is defined as from the location where the cable is connected to the tap, and then from the tap to the ground is C2, and the total C1 plus C2 is a C3. Sometimes some of the tests mention the total capacitance of the bushing, and this need to be also in the spectrum of the manufacturer. So the manufacturer nameplate, we cannot accept more than 10% variation, as we're going to see the tables from different main manufacturers. So that's how we define C1, C2, and then C3 is the total. Another slide here for the same thing pretty much. You got the C3 overall insulation to ground, and then C1 main insulation of the bushing and tap to the ground, which is the C2. So it's just another representation. Next slide will be the bushing problems. So what kind of problems we have with the bushing? Well, multiple problems can happen. Cracked porcelain, possible results, moisture enter in the oil because of the crack, method of detection. And then here we have visual, a power factor test as explained, and hot color test, which hot color test is the actual determination of the leakage current and the capacitance. That's the name of the test, where we actually put some power supply on that tap. we're gonna see details. Deterioration of the cemented joints, moisture again. So the worst thing can happen initially, as initial damage, is to have moisture getting into the tank because of the bushing deterioration. As the designer, the recommendation will be to have the design done with bushing sized to larger than required, like 150%. Is a measure because countermeasure to the deterioration. Bushing is number 3 in the total, so windings will be number 1 in the root cause of the transformer failure. Number 2 will be the oil that is contaminated, and number 3 is the bushing, followed with number 4 tap changer, especially if it's load tap changer. So those will be the 4 main root cause of the transformer failure. Different percentage are given by SIGRE or IEEE, close to each other but not exactly the same. You're gonna see they differ in opinion a little bit in different things. So moisture, visual inspection, power factor, hot color. We continue with gasket. So the bushing is one thing, but then the bushing mounting to the transformer, it has gasket that need to be replaced every 2 years or less, as any material that is non-metal and is deteriorating by aging. Stored or seal leak, broken conductor, voids in compound, oil migration. So is a problem if the bushing is not cooled properly. Normally the bushing on the top of the transformer, it got its own chamber. So the transformer overall, it has 3 chambers: the main tank, the bushing on the top, and then the actual tap changer. Sometimes the top of the transformer for the bushing, it got some nitrogen that is used for insulation and cooling. So the oil need to be present in the bushing all along, so we cannot fail that. If the oil, like no oil you see here, oil leaks out, moisture enters, so we cannot have that. Electrical flashover, bushings are also outside, so remember they are exposed to all the natural factors. I was in an inspection in Ottawa, and they had a 125 megawatt transformer failure because of they don't know exactly what was it, probably a raccoon that walked over the transformer, got zapped, and all it left from the raccoon was the thousands of needles that penetrate, becoming incandescent, and penetrate the actual bushing, the porcelain. So they had to replace that bushing, because even cleaning is not going to give you the surface of the bushing that need to be perfect, like is porcelain, and no asperity, no chips, no cracks, no nothing. So it need to be perfectly clean and shiny. So also you can have lightning discharge that goes to the bushings partially, even though you have surge arresters. Some of that energy may go through the bushing, so may actually stress further abnormally the bushing. Corona is very wetter when you have some initial discharge between the bushing and the ground. Actually is a little bit of a current as a UV, like a light. The camera will catch that and is traveling pretty much along the external part of the bushing. That's why you have the skirts, to try to block those leakage currents that are traveling on the surface of the bushing to the grounded tank. And if that corona is persistent and is high, is actually indication of a damage, and it can be detected through other tests like radio frequency. We will not go there in this presentation, but there are other tests that can be done for specialized test. RRIVs to detect if there is a leakage permanent on the surface of the bushing. Like the example I gave you with the rotten animal that got blown up on the bushing, that definitely will give you a high corona or more. So corona, if it's not addressed, it will deteriorate in a bolt short. So slowly but surely is gonna take that part out and the damage will be severe. Short circuit condenser section and darkened oil. So the oil, same as the oil in the transformer, the main tank or the tap changer need to be at the transparent level, is ASME code for all the parameters that we know for the dissolved gases analysis and so on, or PCBs inside the oil. Anything that is dark means you have sluggish, and that create arc discharge. So the quality of the oil need to be good. Next slide is actually looking at the hot collar test. So here is the way we apply the hot collar test. The measurements can be done in different configurations. We can apply this hot collar connected to a millivolt amps milliwatt meter, and we're gonna measure the actual discharge from the tap to the ground. So that is the GST mode connection. Then you have UST, is a different connection with a ground connected in another way. Pretty much is measuring the same, the capacitance and the leakage current, the leakage power that go through the bushing from the hot collar to the ground. In this case, we actually grounded the top. If you see the top of the connection where normally the cable comes into the bushing is also grounded. Similar, this is another configuration that we can have for hot collar test. Again, we have the millivolt meter, VA, milliwatt meter, and then same deal, we're gonna have a short cable that is connected to the collar, to the tap, that is for testing. And then in this case we have a bypass, a short between the two rings that are on the bushing, if they are available in this case, and then we're gonna measure pretty much the C2 from that one to the ground, because this one is a short on the C1. So C1 is from the top to the actual tap, and then from the tap to the ground. So this is guard mode. There are different modalities of connecting or doing the test. They all do the same actually. Another one here, similar to the previous one, but you can see the second ring is not grounded in this position. We measure the C1. This one is more symbolic and is representing the reading that we're gonna have for the actual C1. So C1 from the top of the bushing to the tap, with the tap grounded. So this is the typical measurement that we do. And the procedure to do this collar test: remove the capacitance of the tap cover, low voltage switch on the power factor test on UST mode, measuring charging current and loss watt, calculate power factor and capacitance at 20 degrees as we said, compare results with manufacturer power factor and capacitance on nameplate. Capacitance should be, so pay attention, the capacitance that we read should be in a plus minus 10% of the nameplate of the power factor of the manufacturer. And yes, sometimes they allow for variation, but not more than 10%. And power factor depends on manufacturer. Sometimes is less than 1% that they allow change. measurement for the C2, right? The C2 test. Now we connect the instrumentation on the tap, and then we got the connection of the instrument to the ground with the tap grounded. Now we measure the other side of the tap from the actual hot color tap connection to the ground, so the other remaining side of the bushing. For C2 we have similar instructions, and I will not read them all. They are here, similar instructions saying again that 20 degrees Celsius need to be corrected to the reading values. Changes 10 plus minus 10% are not acceptable or more. Limit voltages for actually apply to the bushing when you do this test. So when we do the test, we need to apply a source for the leakage current, and that source will be 500 volt for bushing that is less than 69 kilovolts, and 5000 volts for bushings that are greater than 115 kilovolts. Limit test voltage to 2000 volts for Westinghouse type O plus bushing. We will see a table with the actual voltage that need to be applied, and what the manufacturers are allowing for testing, because you cannot apply larger voltage, you will damage the bushing. So those are the voltages recommended generally speaking, but we will see the manufacturer recommendations for each type. Bushing without capacitance or power factor taps. So if you don't have that, then this is a way out to actually be able to connect your instrumentation and to measure the losses in the bushing. Maximum test potential for PF power factor taps. So here we got the manufacturers that are General Electric, Lap, Ohio Brass, Pennsylvania Federal Pacific, and Westinghouse. And then subtypes, what kind of bushings we have from these manufacturers, LC, U, L, and so on. And then the voltage test that we were talking about for measuring the leakage from the tap to the ground is here. So this is the test voltage for General Electric, and Lap is 2000 volts, and then Ohio Brass depends on which type, is 250 or 500, and then Pennsylvania Federal Pacific 500, and Westinghouse 500. So those are the voltages that will be applied in order to measure the leakage current through the bushing and the capacitance power factor. Limits for bushing. So in this table we got the power factor limits for all the General Electric subtypes, A, B, F, L, and so on, and then initial. So very important table. This is telling you what should be the initial value and what is the dangerous power factor, of course at 20 degrees, and when you should consider that bushing damaged sufficiently that need replacement. Don't forget, this is just the limitation, but then you have the ratio that shouldn't be more than 1%. So rate of change. Observe that not all the manufacturers give you both values. Like GE, yes, does a good job and is giving you both. Is giving you the initial brand new bushing, and then on the last column is giving you the end of life value. But if you go to the lap bushing, they give you the brand new, but they don't say anything about when you should consider that bushing end of life. And if we go down, so yeah, the Ohio is okay, but then if we go down to Pennsylvania is okay. Westinghouse is giving you the value for end of life, but is not giving you the values for the brand new initially installed bushing. So not always the data are available. Maybe by calling them up and asking the question, we can find those values, but they are not readily available. Any questions for power factor? So from power factor, now we move to the capacitance, C1. The capacitance measurements are stipulated in the standards, either IEEE 571901 or International 60137, and they disagree a little bit to each other. Pushing for alternating above over 1 kilovolt, and here is the table for C1 acceptance, and that's in percentage. You see slightly different for different type of bushings. They're not too far away from each other, but you can see that they are different. Now which one is the right one, that's I cannot tell you. Usually what you can do when you see something like this, you can take the most stringent, the one that is asking for lower value, and then you are safe, like, you know, IEEE with 0.5, and then the next one, as opposed to take IEEE, you go to IEC and you say 0.7, and again you stay with the international for the last type, the RBP bushing type. It's just an excerpt from a longer table, so I didn't put here everything, so it's from the standards. C1 power factor, so all the limits in table 1 are mean to power factor measured at 20 degrees C, normalized to 20, and change from the initial reading by 1.5 to 2 times. So if a change happen in that ratio, 1.5 to 2 times, warrant more frequent testing. If the change happen more than 3 times, then remove the bushing from service. So it's not just the limit, is the variation of the reading. A change of capacitance by more than 5% is a cause to investigate the bushing. These guidelines are in line with IEEE guideline for apparatus bushing. So that's the standard from where this variation in reading are taken. Taps and power factor electrodes. So capacitance taps and power factor test electrodes check to determine proper grounding. So a lot of the time, and it happened to us as well, by not connecting properly the grounding and the instrumentation to the tap, can lead to a wrong reading, and definitely the conclusion will be you know, not correct, that the tap is damaged. Eventually is not. And if you redo the test, we will see is actually in perfect order, but the test was wrong, and because of the connection of the instrumentation to the tap and to the ground. Interpretation power fact test, including the hot collar test performed on similar type of bushing, should give you on similar weather and temperature conditions, should give you the same value. So when you measure the bushing on 3-phase high voltage, they should give you similar values, and if you do that on the low voltage, they should give you similar values. Even similar transformers should give you the same if the same manufacturer is used, the same manufacturer provide the bushings. This is a regular test. It should come up in a yearly test, but not sure how we have the collapse here. It should be done at new installation after a severe stress of the transformer, and also whenever, you know, maintenance is performed on the transformer. Definitely replacement of the bushing. The loss of oil or compound may be detected by comparing the hot collar test current that rated than power factor. So abnormal low value for the hot collar capacitance, 10-15%, may indicate absence of compound or oil. Testing under successively low petticoat skirts will show normal current reading when you go closer to the ground. So that means not the complete bushing is in oil. So that's how you detect that, by moving the reading down to the ground. You can repeat the reading in different positions. Modern oil impregnated paper insulated condenser type bushing have power factor 0.5 or less at 20. Any such bushing which show a significant increase should be investigated. Usually the capacitance or power factor of the bushing are provided by the manufacturers. We're going to see the nameplate data for our transformers. Another interpretation here, similar to the previous ones regarding the power factor. This one is, we go to the next type of test, which is after we discuss the power factor and the capacitance. Now we move on to the actual dielectric power factor, dielectric frequency response. What is the dielectric frequency response? Is nothing else but the power factor reading a different frequency. So if you look at the bottom on the axis of this graph, we got frequency from 1 millihertz, so 001 hertz, up to 1000 hertz, which is 1 kilohertz. So from 001 to 1000, we performed the same power factor test, applying those voltages that we talked about, but now we changed the frequency. So the voltage, as you remember, depending on the manufacturers, can only be up to 2000 volts for G, and then Ohio Brass you have 250 and 500, and all the others are 500 AC, but is not 60 hertz here, is actually 60 will be somewhere here between 10 and 100, right? So that will be the area where we read at 60 is one point on this graphic. A single point that we had before the reading is going to be on the graphic, but as you can see, is normal that enlarged frequency response on the very low frequency, we're going to have a higher dielectric power factor. So you see the losses increase at low frequency, and then they decrease in after 1 hertz is coming back down, you know, in that area 10 hertz and above 10 hertz we are in the range that we are used to see the power factor. So this is a dielectric frequency response, and you have two types. Is the narrow band NB DFR, that is only considering the test from 1 hertz to 1000. Is not going through or even less than 1000. It's not going through the low frequency response that we have on a complete dielectric frequency response. And there are charts and recommendations from Doble, and we're going to see those recommendation values. Narrow band typically perform at low voltage, so for narrow band typically we apply 250 as a low energy test. It is safer to perform. Allow visualization of unique dielectric signature of the object tested. Therefore, graphical comparative analysis between system bushing mounted and common objects is possible. So you need to be familiar. When you have a new transformer, you need to do this test and have a base, so that will be used as a starting point. Eventually you have some data from the manufacturer that they did for the factory acceptance test. Those will serve from the bulletin. They will serve as an initial starting point for the graph. Again, the three phase should be pretty much close to each other for the same bushing types. And yes, we don't install different manufacturer on different phase. We will have all the same. DFR curves at different temperatures. So as we said, we want it at 20. So as you can see here, the response for dissipation factor in brackets tangent delta is actually the bottom line. The lower line is only increase at the end, and then we have the same test at 60, at 40, 60 and 80. So at 80 degrees you can see that the actual dissipation is the highest. So we can conclude that pretty much at least on the low frequency under 10 hertz, the temperature creates larger dissipation. and then higher than 10 hertz, from 10 to 1000, then they are kind of in the same range, and we cannot conclude that the temperature brings up. It actually lowers, so a little bit lower than the 20 degrees. That's the graph, so keep in mind, if you do complete dielectric frequency response, everything that is on the low frequency will be highly influenced by the temperature, and it will have some influence on the 60 hertz as well. As you can see, 10 to the power of 2 here is 100, so even at that temperature you can have some influence. That's why we need to scale it down to 20. Power factor analysis. So here is actual reading from the main output transformer. We can see here the nameplate data in power factor in percentage. So the nameplate data is actually asking for 0.23 for phase 1, 2 and 0.24 for phase 3. And the measured power factor was 0.47 on A, 0.27 on B, and 1.4 on C. Okay, so definitely they don't look good on phase A and C, especially on phase C. But we will see the root cause of this. So temperature corrected power factor, so after the correction at 20 degrees, at 60 hertz, phase A 0.54, at 10 hertz 0.55, and 1 hertz 1.32. So it's not a complete graph, but there are 3 measurements taken on 1 hertz, 10 hertz, and 60 hertz. These are the value on the high voltage side pushing. 1 hertz bushing power factor percentage, so bushing condition. This is from Megger. So Megger and Doble are the 2 companies that has the most experience and the most database for the testing they did. And we can see here the bushing condition as new, good, average, and investigate. This come from actual Megger company. 20 degrees and test at 1 hertz, they recommend these values. So as new will be between 0 to 0.5, good 0.5, 0.75, average, and then investigate everything that's lower than 0.15 or greater than 1.25. DFR, dielectric frequency response analysis that we got on the same 3 bushings on the MOT. These are the graphs for the 3 phase, and we can see that 2 of them are pretty close to each other, the same shape, but one is way off, higher values and different shape. DFR results and acceptable limits. Here we got basically conductivity and Megger values in percentage that indicate contamination. So recommended values. So the results were obtained from the full DFR analysis shown in table 5. The limits for the percentage, MC, and conductivity of the oil proposed by Megger is in table 6. Final assessments. So all the results together here, we got the all the tests done on the 3 bushings. Some are bad results according to the IEEE. Chigre TB445 is saying is okay. And then at the end, after the power factor and all these tests, leakage test and capacitive test, millicoulomps, so those are MC, we have the average, or investigate. So that was the final conclusion here. However, MOT bushing nameplate is this. So on the unit 0, Bruce A, we got these values for the H1 bushing, and you can see here capacitor 1 in percentage, then capacitor in picofarads 788, capacitor 2 from the tap to the ground in percentage, and 7268 picofarads, and then the rated kV 485 kilovolts and amperage 3000 amps, and the manufacturer is ABB, serial number and so on. So we got all this data from the manufacturers, which is ABB, and then we got this one that is showing the actual reading that was done at different voltage. So on the same bushing that we saw before, the actual nameplate data, these are the readings for 500 volts, 1000, look at the second column, 1000 volt, 1500 and 2000. So it's, yeah, 1499 and 1999. So increasing the voltage at 60 hertz, these are the results that we found on pushing on H1 according to Doble results. And then what we have here also is the C1 and C2. So we can see the capacitance, right? C1 and C2. The results here is for different frequencies, so the same test but now applied for the same bushing with 2 kilovolts, and frequency was increased from 15 hertz, then 40, 57, 63 and 70. And these are the results with the power factor, the current applied, and then the total current, and then the capacitance in picofarads. So that concludes here the bushing on C2, manufacturer ABB, and that's on the secondary. So now we have the 245 kV. Sorry, it's the same bushing on the H1, but it's 245 kilovolts from the tap that you can apply. And Megger on C2, here are the values in power factor, capacitance, nameplate data on the left, and measured data on the right, and that is for C2. So H1 look pretty close to the manufacturer data. However, DFR, dielectric frequency response, for the same H1 bushing high voltage, we can see the curves here, from 10 millihertz to 1 kilohertz. And then the Doble test for second transformer, so this is 2, unit 2, we got H1 again, nameplate data, and then bushing additional H1. That's all nameplate data for this transformer. And for the transformer unit 2, we got these results for C1, C2. So if we look here, we got capacitance and C2 test for 500 volts, 1000 volt, 1500 volts and 2000, similar to what we did for the previous one, to compare one transformer to the other. And this is the capacitance that was readed and the power factor for different frequency. And then we got the transformer frequency response for 15, 40, 57, 63 and 70 at 2 kilovolts, and this is the power factor that we read here on this transformer. And definitely these are the Bruce A unit 2 results from the Megger. We can see here the actual manufacturer data, the H1 on this transformer, and then the next one will be the power factor, nameplate data and measured data, which you can see the problem here. The power factor is actually few times higher, so the manufacturer data is asking for a power factor 0.344. We found the power factor is 1.6. So we're gonna see that was a bad reading, and it wasn't actually a real bushing defect. But for the moment when the reading was done, we were unsure what actually happens, so we could not energize the transformer. So that's the bottom line. When you have this kind of readings, you cannot do anything but repeat the test, try to correct the installation of the probes, and if you have two good readings after a bad readings, and you can explain why the bad reading happened, then you can actually apply power to the transformer. So this is the DFR for this bushing, and this is the actual conclusion on transformer 2. The red phase fail. Test will be repeated. As we said, we clean the tap, like the bushing, with the alcohol and dry out. We clean the black resin that was present around the bushing. Verification of the grounding on all bushing connections. Some intermittent noise was present on the tank during the hot color test, so you can see that on the actual signals that there was an intermittent connection, so bad connection with the grounding. Double test repeat. After the repeating the double test, we actually find out that the results are fine. So we can see here that the actual C2 is very, very close to the actual manufacturer. So we did the test again at 500, 1000, 1500 and 2000 kilovolts. So the results you can see here are very similar. So you have the nameplate data and then the reading data, capacitors in picofarads, and then the actual capacitance reading. Even the name of the technician who did the test. Double test repeat after grounding leads were tied up, and yes, we have again the H1 bushing, additional readings, same voltage from 500 test, 500 volts, 1000 volt, 1500 volt and 2 kilovolt. And here are the reading. You have the dissipation, the milliamp currents, 28 milliamp, is not dependent so much on the applied voltage, you can see. And then power factor 0.348 is pretty much stable. Then we have the capacitors in picofarads, the same, and is declared as good. So basically we passed the test after corrections and the cleaning of the bushing. Winding temperature is just the instrumentation that is available on the transformer. And the next two pictures actually is going to show you how we apply the collar on the tap for the bushing test, applying those voltages and reading the leakage current, the dissipation factor or power factor, and reading the capacitance. This is another one after cleaning, how it was actually applied, the correct test. And the third one, right? So this is the installation of the bushing collar, and that will bring us to the end of the presentation. Do you have any questions regarding the test? Any questions? Any question is a good question. Anybody?
Where can I read more about these bushings? We're currently designing some for PHT pump transformers. You must have mentioned a IEEE standard. Sorry, I might have missed that.
Yeah, we have mentioned here too, is actually the two standards, the IEEE and the actual international standards. We will focus on the IEEE, but also you need to have the manufacturer data for your bushing, nameplate data. Another reading you can do is on the, you see here are the two standards that I mentioned, 571901 and then 60137. But Megger and Doble they do have a lot of information on their website that may help with the interpretation of the data. But these are the standards. We do have access to the IEEE. I'm not sure about the IEC.
Perfect. Thank you.
Thank you. Good question. So any other question? Any question is a good question. So once again, going back, what we went through is the test that we need to do to test correctly the bushing as a minimum is the capacitance C1, C2 from the top to the tap and from the tap to the ground. Then the power factor and dissipation factor, so power factor, tangent delta, dissipation factor, all at 60 Hertz. All these readings are at 60 Hertz, but then we have dielectric frequency response that is for a range of frequency. And we should have graphics that can be compared to the readings. So don't forget this slide, that is crucial to understand what we are reading and what kind of values we want. Any other question? Yeah. Well, another conclusion that we should take away is that need to be very careful with the installation of the instrumentation on the bushing, and the bushing itself that need to be very clean and no sluggage around. As you can see, they cleaned the bushing with alcohol and they removed any sluggage that was from the installation or just because of the usage. So sometimes you are testing the bushing on a transformer that was in operation for a while, so you may find different compound that is there, and it should be removed before you actually test the bushing. But if you find in excess these kind of things, maybe you have a problem with the installation of the bushing and the gasket, and that should be also revisited. Yeah, so bad results were not bad results in this case, were actually wrong readings, which may happen. Okay, last chance. Any other questions regarding the bushing testing? If not, I will just remind you that this is very similar to what you may hear from others. They perform on the insulators, at least leakage current and tangent delta, power factor. Surge arresters, they perform kind of the same test, but they have different acceptable values. And yeah, on surge arresters you may also have functional tests because they usually more than one time, so they can support a certain discharge for hundreds of times typically, but any test can actually shorten the life of the surge arrestor. Okay, thank you very much for attending this webinar, and that was webinar 64. We will continue next week. So now I find out a way to actually have the recording for you on the internet, so I will continue every week probably. If you have a topic that you wanted for the next week, let me know, send me an email, and I will do my best to accommodate. Thank you again, and have a nice beautiful day. Thank you. Bye now.